Morning, and I suspect I'm between you and your lunch. So we'll try and make this interesting. We all love stories. Human beings love stories, and that is the best way that we learn. So let's start with the first story here today on this topic of rethinking adoption. The story from China, where one of the ways in which the government there discourages jaywalking is by capturing pictures of people that are jaywalking and displaying them on billboards, shaming people. So the picture of Dong Mingzhu, who was the chairwoman of Gree Electrics, was displayed on one such billboard because the AI thought that she was jaywalking and crossing the road. It turns out she wasn't even in the city. What happened here was that the AI recognized her face correctly, but it picked it off the back of a bus. So there was a picture of her on the bus. It identified the picture, concluded she was jaywalking, and her picture was put up on the billboard. So the AI recognized the person correctly, but the outcome was horribly wrong. In 2008, Google launched Google Flu. The idea was that Google has access to tremendous amount of data that people are searching for, and from that, Google can make reasonable estimations of where there are likely to be flu outbreaks. And this model worked reasonably well till Google changed in 2011 its search method and started providing people prompts. And that changed the underlying data. That changed the way that people were interacting with the search engine, and that changed the underlying data. And consequently, the model started to fail. So the AI was working, the modeling was probably working, but the models failed to take into consideration that the underlying data structures were changing, and possibly the relevance of the queries also started to change. Subsequently, Google closed this application down. And then I want to talk about this third story here of the very famous Google Glass that was launched in 2014. And the promise was that it's going to revolutionize our experiences and the way we interact with each other by providing us real-time information about the places that we were in, the people that we were interacting with, so on and so forth. And Google Glass, in its initial launch, was a failure. So much so that certain bars, restaurants barred people from entering it if they had Google Glass on because people were deeply suspicious. What are you doing wearing that? Are you spying on me? Are you going to take pictures of me? People weren't quite sure as to why this equipment existed. So here was a fantastic piece of technology looking for a solution. So no clear solution, no clear problem to solve, but a great piece of technology. And why are we talking about these three stories, right? We're talking about rethinking adoption of AI. We care about adoption because adoption leads to value creation. So I'm going to share with you today 3 equations for creating value from AI. Think of these as pseudo equations. They're not really mathematical, but just sort of, ways for us to understand the underlying concepts over here. So here's the first one. That results are AI times engineering times design. The value that you can get of the results of any sort of program is a function of bringing all of these 3 together, and the effect is multiplicative. And we'd like to submit that engineering and design have a disproportionate impact on the results that you create. Just AI is not enough to create value from AI. We need great AI. We need tremendous amount of data that is accurate, that is timely, and we need design that is user-centered. So driving results at scale requires these three things to come together. Algorithms that match or exceed human performance, engineering that seamlessly connects data, builds pipelines into algorithms, and is able to automate and scale decisions in real time and at scale. And design, which really means framing and solving problems by putting the human at the center of the decision, taking human behavior into consideration, and being able to drive adoption through superior end-user experience. So that's the first equation. And we'll speak more about this as we go forward and as to how we bring this together. Apple launched Siri in 2011. And the initial experiences were quite poor. Siri was unable to understand us very clearly and misunderstood us several times. And then it was not yet ready for contextual awareness, right? So here you get some really crazy sort of, outcomes. Someone says, I'm going to jump off a bridge, and Siri says, okay, here are the different bridges that you can go to, right? Or the application was, rude. Of course, we all use Siri today, and we know that the experience is completely different. And so we would say, what happened here, right? And this is really about error in our AI applications. We need to bring the errors down. If we want people to adopt the AI and we want there to be trust in the AI, we need to bring errors down. But what is the way that we can bring error down? So that brings us to the second formula. Again, it's not a mathematical formula. It's just a way for us to absorb the concept here. Reducing error is a function of data, compute, and the techniques that we use. Okay? So we need a lot of data for these algorithms. We need data in different contexts. We need data to be real-time. We need data to be live, right? And that means that when we are thinking of any application, we need to think of all the ways in which we can feed those applications with data through which those algorithms can learn. It means we might need to put more sensors. It means we might need to look at alternative sources of data, even synthetic data. If you look at the field of image analytics, you may not have enough images, but we can convert those images or create multiple images by doing things to those images which we experience in real life, distorting those images, putting them at different angles, just to give you some examples, right? And experimentation. Test control experiments to create outcomes that we may not observe enough of. We do that through experimentation. We need to have a lot of computational power to be able to run these, right? Cloud compute, edge compute, these are all new techniques that are helping us do that, technologies. And then multiple different techniques. The field of AI has expanded, the progress has been tremendous, and we need to bring all of these different techniques from structural models, statistical models to generative AI, neural networks, and all of that to get us to a place where we can get lower and lower error in the algorithm so that we can drive better and better trust and therefore adoption. Some of us are aware of this application called Recognition AI. Amazon had launched this, and initially police departments, governments, etc. were using this to recognize people, to do facial recognition. In 2019, a couple of scientists did some research on this, and they were able to show quite conclusively that the algorithm was almost 30% less accurate in identifying darker toned females. Some further research showed that this was most likely because these organizations had much fewer number of darker toned females. Now, this brings us to the idea of governance. And yes, when these studies were published, Amazon withdrew the product. Microsoft went on to say that they're not going to sell their products to police departments and all of those areas yet, right? But these kinds of things can happen in any of the applications in something as simple as doing a loan approval or how we do marketing or any of those areas. The biases that we carry, the environment that we operate in, the algorithms will learn from, and they will reproduce. And that brings us to the third equation, organizational effectiveness. And that is a function of the talent that we have on our teams, the culture, and the governance that we put around these programs. All of us are aware that it is a talent war there for top-notch AI engineering or design talent. So we need game-changing talent. We need interdisciplinary teams. And if we need our AIs to replicate what's happening in society and be fair and inclusive, then we need diverse teams so that those algorithms can learn from diverse perspectives and are not biased in one way or the other. It's a new field. We're experimenting. We're figuring out new things. And therefore, we need a culture that is based on idea meritocracy, not necessarily on seniority. We need a culture that's a positive error culture, a culture that understands that there are going to be a lot of errors, there's going to be a lot of experimentations, many of them will fail, but the experiments that do succeed are going to transform the way we do business and the kind of outcomes that we deliver to our stakeholders. And lastly, governance, which is probably the most important out of this, because lack of governance can destroy faith very, very quickly. And that means no adoption, that means no value, right? So how do we productionalize these? How do we ensure that we are deploying AI in a responsible manner? So these are the three equations. We put them together. Results, it's a function of the quality of our AI, engineering and design, where we submit that engineering and design have a disproportionate impact, and those are areas that we need to focus a lot more on. Error, function of the quantity and the quality and the diversity of data that we have, the compute powers and the techniques that we apply, and organizational effectiveness, function of talent, culture, and governance. And as we think about adoption, and as we rethink adoption in our organization, how do we use these equations? And the first place I want to go to is design. We'll speak of error, and then we'll speak of governance, okay? But how do we, as organizations today, attempt to drive adoption? What are the tools that we use? We use rules and mandates. Expenses must be submitted by the 7th of the month, or else you cannot submit them, right? We use rewards and penalties. And we use awareness and education. All are important tools. However, they're not sufficient. And they're probably not the most effective either, because they speak to a very small portion of our brain. And we'll talk about that a little later. But I want to talk about one example here of Cure.ai. It's a product that Fractal Analytics, our company, released some years back. It is known that radiologists misread about 23% of the X-rays. Because they miss out something. The human eye cannot perceive certain things on the X-rays. They're overburdened and so on. So there is a 23% error rate. It's just well established and known. So we created Cure based on deep learning algorithms, reading about 8 million X-rays that we had procured from various partnerships, and developed an algorithm that was able to diagnose disease states from chest X-rays at higher accuracy than radiologists. And we thought that, wow, this product is going to take off. Everyone's going to want this product because we have solved this problem. In a fraction of a second, you get a diagnosis much more accurate than what can be got through radiologists. And we were in for a rude surprise. We just kept knocking and knocking, went to various hospitals, doctors, radiology labs, and so on and so forth. We got no traction. because people weren't really interested in that product. They didn't see a way to fit that into their workflow. Perhaps there was some, fear. Is it going to replace me? Or honestly, okay, I know I'm good enough. It doesn't really matter if I get 5% more accuracy. So it became another case of a good technology with no use, with no apparent use case for the people that needed it. And then we had this breakthrough. So tuberculosis is one of the leading causes of disease-driven deaths in South Asia. And a vast majority of the global instances of tuberculosis are found in South Asia. The government of Philippines instituted a program where they were sending vans into villages with X-ray machines in them to scan people. Now, money buys you X-ray machines and it buys you vans. It does not buy you radiologists. So what would happen is that they would collect these X-rays, they would send them back to the city where the hospital was. It would take 3 to 6 weeks for the results to come back, in which time if I had the disease, it could deteriorate, it's transmissible, I could give it to someone else, or I may never come back to collect my diagnosis. And this is where the opportunity was for that product. So we embedded Cure into the X-ray machines. Now, as soon as the X-ray is taken, there's a diagnosis right then and there. Okay, and the person in that who's a technician is able to tell the person, you're good, come back after 1 year for the next screening, or go see a specialist. So the use case was different. People here were not looking to treat. It was more like a screening device. And our learning out of this was that successful AI implementations are user-focused. They're decision backwards and they're narrowly framed. All of which was satisfied in this application of Cure. They were user-focused on the technicians that were doing this, right? Because they didn't have the ability to scan to provide the diagnosis. They were user-focused on the patients or the people that were coming in for the screening who couldn't wait for 6 weeks to get the results. They were decision backwards. We said, okay, we need a result now, and we're not looking to treat, we're just looking to screen. So a doctor is still going to do the treatment. This is just doing a screening. And it's very narrowly framed. We just framed it for tuberculosis and tuberculosis alone. There was a program there that wanted it. And now this is taken off. It's very, very successful. So when we speak of design, we're saying that design means that our AI implementations need to be user-focused. They need to be decision backwards, not technology forward, and they need to be narrowly framed. And now come back to the example of Google Glass. Google Glass today is being deployed with doctors, with the idea of being able to provide doctors real-time information on the glass, being able to help them transcribe the notes because they spend a lot of their time actually taking down notes, right? Enabling them to not touch their computers and phones, which have a lot of germs. And then some doctors are saying that it's finally allowing me to look my patient in the eye, look up from the computer and look at the patient in the eye. So here Google found a application, a solution for their technology, and now you're looking at success. So what we say is that we need to incorporate human behavior into shaping the environment. And when we talk of things such as rewards, penalties, etc., they're all focused on the rider. And so this is a depiction of the human brain, okay? The rider is a very small part of our brain. It is the rational, logical part of our brain. It's a new brain. It's skills that we have developed more recently. But the larger part of brain is still what we call the elephant. It's the emotional brain. It's the brain that has learned to respond in very simple ways because that's how evolution over millions of years has taught us to be. Most of the things that we do are targeted at the rider, but not at the elephant. But we need to reverse it. We need to focus more on the elephant that is emotional, that looks at non-conscious communication and responds in more simplistic ways. So one of the big issues with in the medical field is non-adherence to medication. About 6-7 years back, we built these models to predict who is going to miss their medication, who's not going to adhere to the medication, because people who have to deal with chronic diseases have a big amount of pill burden. Okay, and that model we were able to predict with fair degree of accuracy, but it really didn't change anything about adherence to medication, because the issue was that it was not about prediction. The problem was not with the prediction. The problem was with making it easy. When people have to consume tens of pills 3 to 4 times a day in different combination, it gets complex, people forget. And so then came pill pack, right? They solved this problem very, very elegantly. And they started creating a pouch for every single time when you needed to take the medicine. So now you get this beautiful little strip, okay, has the date and time when you need to take it. And if you missed it, you know I missed it because I didn't open that pack. And on the same line, I want to talk about one application from Fractal. This is something that we have implemented for in India. One of the big causes of deaths in Mumbai city is people trying to cross the railway lines, which are unguarded. About 10 people every day die because they're trying to cross this railway track and they get hit by a train. The analysis showed that these are young people, typically male, 18 to 35, and the deaths are taking place in broad daylight. So it's not an issue with infirmity of mind or body. It's not an issue with lack of visibility. So what really was the issue? And the issue was that the human brain is incapable of estimating the speed of fast-moving objects because we have not seen them through our lives. We have seen small animals, deer and rabbits that we've been hunting for several thousands of years, and we know how to estimate their speeds. Planes, trains, these are all new things. And so then how do we deal with this, right? And one of the ways in which human brain estimates speed is relative, through a relative guidance. And so we came up with the idea of painting the tracks yellow and leaving some gap, then painting them yellow. And now when the train goes over those tracks, as those yellow lines disappear, it sends a non-conscious communication to the brain as to how fast that train is coming. So you look, you see the yellow lines disappearing, and you step back. The places where this was put, the accident rates dropped by about 70%, right? You could have put a sign, be careful while crossing the train tracks. It would not have made any difference. So, coming back to these equations, user-focused, decision backwards, narrowly framed, but to get the best results, leverage behavioral science and design principles. Incorporate that into what you do. And now going back to the Siri example, accuracy is important. And so in the world of speech-based search, when it came out, initially the error rates were much higher than human level. Around 2015, the error rates for speech recognition actually started to become lower than human levels. And that's when adoption of speech-based search really took off. And the principle there is therefore is that whenever we're using AI, we need to create, match, or exceed human capacity. Okay. This is an example of an application that Fractal has implemented with banks on conversational AI. With HDFC Bank over here, 16 million queries per month, thousands of types of questions. But again, the critical reason why this has taken off is because we have an accuracy of well over 95%. And that accuracy is critical. And now I want to come to the last one around governance, right? So this is a story of Clever Hans. Sometime in the 19th century, there was, in Germany, there was a horse called Clever Hans. And his owner would take it to various places and ask the horse questions. Example, okay, if Tuesday is the 8th day of the month, then what day is Friday going to be? Okay? And the horse would reply with taps of the hoof and the way it would nod its head and everything. And over course, people started to think that this horse was really, really clever. It was doing intelligent mathematics and all of that stuff. Subsequent research showed that actually the horse was simply responding to non-conscious cues that its owner was giving. Even the owner may have been unaware that he was giving the horse those cues, but the horse was really responding to those cues, wasn't really doing the intelligent mathematics that everyone thought that the horse was doing. And how's that relevant? So in the case of Cure, when we initially built the models on a very small set of data, we were shocked by the accuracy that we got. We were getting nearly 100% accuracy. And we could not kind of figure out. So I said, we've got to go explore this. There's something's probably wrong over here. And what we discovered was that our algorithms weren't actually reading the disease. These X-rays had been annotated by doctors. Okay? So if there was a disease on that state on that X-ray, the doctor had already marked it off. And all that the AI was doing was it was actually reading that a doctor has annotated that X-ray to already be having some disease state, right? So that's all that it was doing. And that, when we caught that, we had to go back and get X-rays that were not already giving us signals and then rebuild all of this, right? And that governance is critical because we'll see that often that the way we input the data and the kind of governance that we put around that is going to drive outcomes. So that really is, I just shared one slide over here around how one should think about a responsible AI. But really, I think there's a lot over there, but just want to talk about the foundational principles around making this transparent, creating accountability for what we do, respecting privacy and safety, and ensuring fairness and inclusion. So with that, on the third equation, as we focus on governance, okay, design for robustness, design for fairness. And that really is, in summary, in one slide, our recommendation or a suggestion on what we should be doing to rethink adoption. Focus on results, which means that AI engineering and design really make sure that the applications are user-focused, they're decision backwards, narrowly framed, and use design principles to create the applications. Make sure that the algorithms match or exceed human capacity, human accuracy, and then design it for robustness and fairness. Thank you.